Okay, in this lesson, we're going to talk about properties of solutions. At the end of this lesson, you should be able to express concentration in various ways. You're going to be able to calculate the amount of solute present in samples of solutions of known concentration, determine the amounts of solids and solvent needed to prepare solutions of desired concentrations, describe and calculate concentrations of molecular and ionic solids, describe and calculate colligative properties of solutions such as vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure, determine the molar mass of solid particles from colligative properties, and use Henry's law and Raoult's law to describe solutions with volatile solids. Okay, so we're going to start by talking about concentration because properties of solutions generally depend on its composition, how much solid and solvent you have. So how do we express concentration? The most common ways of expressing concentration can be classified into two types. Okay, one is first of all, okay, concentration tells you the relationship between the amount of solute or solvent, usually we deal with the solid in the numerator, to the amount of solvent or solution. So it's a ratio of two things, okay, amount of solid or solvent compared to the amount of solvent or the entire solution in the denominator. In type 1, one type of concentration unit that's commonly used involves the use of volume of the solution in the denominator. So for down here for the denominator, if you're using volume there, these types of concentration units depend on temperature because, as we know, things expand when the temperature increases and generally contract when the temperature decreases. So the kinds of concentration units that use volume of solution in the denominator are molarity, milligrams per deciliter, percent weight by volume. So this W/B here, weight by volume, percent by volume. Okay. Second type of commonly used units for concentration is one where everything in the concentration units involve mass or moles of solvent or solution. So these are concentration units that are independent of temperature. The amount, the mass, and the moles of substances do not change with temperature. So we're going to talk about molality, mass percent, also known as percent by weight, mole fraction, parts per million, and parts per billion. So let's take a closer look at type 1 concentrations. Molarity is defined as the amount of solute in moles per liter of solution. Okay, so it's also millimoles per milliliter of solution. Percent by volume is percent weight by volume is a concentration unit that tells you the amount in grams, the amount of solute in grams as a percentage of the volume in mils. So it's really grams of solute in 100 mils of solution or grams of solute in a deciliter of solution. 1 deciliter is 100 mils. Okay, so you can calculate it if you know grams solute, divide by the mils of solution, and that gives you grams per mil. So if you want to know grams per 100 mils, you multiply that by 100. So if you just use unitless quantities for grams and milliliters, and you multiply by 100%, you get that's percent weight by volume. Okay, so vinegar, for example, the kind you can buy at the store, is 5% weight by volume acetic acid in water. That means if I had a 100 milliliter sample of that vinegar, okay, 5 grams, I'm going to have 5 grams of acetic acid in that particular sample. Now, an intravenous glucose solution is also 5% weight by volume glucose. Physiological saline solution is 0.9% weight by volume sodium chloride. Another commonly used unit for concentration, this is particularly common for in cases where you have a mixture of liquids, okay, such as alcohol and water. And percent by volume, so that's what that V/V means. So you have volume in the numerator, volume in the denominator, is a ratio of the volume of solute to the volume of solution as expressed as a percentage of the volume of the solution. So the volume of solute present as a percentage of the volume of the solution. total volume of the solution. So if you take the milliliters of solute divided by milliliters of solution, as long as those two have the same units of volume, just multiply by 100%, you get percent by volume. Another way of thinking about it is really milliliters of solute per deciliter of solution. Remember, deciliter is 100 mils, okay? So, for example, liquor that is considered to be 100 proof in the U.S. is in fact 50% defined to be 50% by volume ethanol. It has ethanol that's 50% by volume. A commonly used unit in medicine is milligrams per deciliter. So that tells you how many milligrams of solute you have in a deciliter of solution. Blood glucose levels, cholesterol levels, your cholesterol number, that's actually expressed in milligrams per deciliter. So let's apply these definitions to some simple examples. Let's say you have 5.844 grams of sodium chloride. You mix it with enough water to make a 200 ml solution. Okay, so imagine you have here a flask. You put some 5.844 grams of sodium chloride, and then you add enough water to it. You bring it up to a total volume of 200 mils. What was the molarity? Okay, let's go look at the defining equation. Molarity equals moles of solute, so moles at NaCl. I'm going to use the letter N to represent moles, over volume of the solution in liters. Okay? So this becomes, how do you figure out moles of sodium chloride? You have to change grams to moles. Let's change grams to moles. What information do you need? Molar mass, right? So molar masses, sodium, if you look it up, is 22.99 grams per mole. Chlorine is 35.45. So 58.44 grams per mole is the molar mass of sodium chloride. So if you want to convert grams to moles, you just divide, right? So you say 5.844 grams NaCl times 1 mole NaCl over 58.44 grams NaCl. Okay, so that should give you 0.100 moles. Okay, so number of moles of NaCl is 0.10. So 5.844 is a tenth of 58.44. Okay, so 0.1000 moles of NaCl, okay, per liter of solution. And what's the volume of our solution? It's 200 mils. Okay, so that's 200 times 10 to the negative 3 liters. Anytime you see milli in your unit, if you want to get rid of that milli, simply replace that by 10 to the negative third. Milli means 10 to the negative third. So our volume is 200.0 times 10 to the negative 3 liters. A note about Sig Figs here, 5.844 grams has 4 Sig Figs. Okay, so when you convert that to moles, you should have at least 4 Sig Figs in your molar mass. Okay, you generally have it. You need at least 4 Sig Figs for our molar masses when we do calculations. So the answer there would have 4 Sig Figs. That's why we have to write this with 4 Sig Figs. Okay, so 0.1000 divided by 200 times 10 to the negative third. That is 0.1000 moles of NaCl over 0.2000 liters. So that's 1/2. So that would be 0.5. 4 Sig Figs, so 0.5000 moles per liter. Okay, let's take a look at this clicker question. Which of these has the highest molarity? 0.1 mole sodium hydroxide in 100 mils of solution, or 0.05 mole sodium hydroxide in 100 mils of solution, or C, 0.10 moles of sodium hydroxide in 50 mils of solution. Now you could do the calculation for molarity for each of these, but you really don't have to. All you have to do is compare. Okay, so let's compare A and B. They have the same volume, and if you recall, molarity is moles sodium chloride moles of solute, which is in this case sodium hydroxide, I'm sorry, divided by volume in liters. Okay, so for the same volume, the bigger the number of moles of solute, the higher the molarity. So between these two, which one has a higher molarity? A would have a higher molarity, so B is not correct. Okay, now let's compare choice A and choice C. Here you have the same number of moles, 0.1, so the same N, but choice C has a smaller volume. The smaller your denominator is, you're dividing by a smaller number, you get a bigger number. So choice C will have a higher molarity. Okay, so for same number of moles, a smaller volume will give you a bigger molarity. So choice A is wrong. So correct answer for this one is C. How about this one? Which one has a higher percent weight by volume? Oops, I'm sorry, I forgot percent weight by volume in an earlier problem. Okay, you're supposed to calculate molarity and percent weight by volume. So let's do percent weight by volume here. It's a definition of percent by volume. Percent weight by volume is grams, so I'm just going to use G of your solid, grams NaCl, over volume in mLs of solution, in mLs, times 100%. Okay, so the mass of the solid as a percentage of the volume in milliliters. So in this case, you have 5.844 grams, and we're just going to do away with the units here since this is a percentage. And volume in this case is 200 ml, so divided by 200.0 times 100%. And that should give you what's 5.844 divided by 200 times 100. That gives you 2.922%. Okay? Weight by volume. And just like I said earlier, this is the same thing as grams per deciliter. Let's do that in terms of grams per deciliter. If you have 5.844 grams over 200 mils, okay? A milliliter, a deciliter is 100 mils, right? So 100 mils is 1 deciliter. So that cancels milliliters. That gives us the same answer, 5.844 times 100, okay, divided by 200, and that's 2.922 grams per deciliter. So you can see percent weight by volume is the same thing as grams per deciliter. All right, so let's go back to this question right here. Which has a higher percent weight by volume? 5 grams NaOH in 100 mils of solution, or 5 grams sodium chloride in 100 mils of solution, or is it neither? Which one? What's the definition of percent weight by volume? It's grams of solute over volume in milliliters of your solution, right? So times 100%. So you have the same grams and the same volume of solution, so that means they have the same percent weight by volume. Okay? What about this question? Same question, same choices, but which one has a higher molarity? Okay, then you have to remember molarity is moles over volume. Since we have the same volume here, we're really being asked for which one has more moles, right? So 5 grams NaOH versus 5 grams of sodium chloride. Which one has more moles? Then you have to convert this to moles. Okay, sodium hydroxide, molar mass. Sodium, you look it up, it's 22.99 grams per mole. Oxygen is 16.00 grams per mole. Hydrogen is 1.008 grams per mole. So this is going to give you 40.00 grams per mole. So multiply by 1 mole over 40.00 grams. Whereas this one, sodium chloride, we've done this earlier, 22.99, and chlorine is 35.45. That gives you 58.44 grams per mole. So multiply by a mole over 58.44 grams. Well, okay. Which one's bigger? You're dividing the first one by a smaller number, so this must be bigger, right? So that will have more moles of solute, so it's going to have a higher molarity. See, you're dividing this one by 40, whereas this one you're dividing the same number by 58.44. So if you divide by a smaller number, you get a bigger result, so more moles for sodium hydroxide. So the correct answer is A. Okay, let's take a look at type 2 concentration. In type 2 concentrations, like I said, all of your quantities used to express the concentration are either mass or moles. So these are independent of temperature. So molality, note the difference there between in the spelling. Molality, that with the L, whereas the earlier one we talked about was molarity, is defined as moles of solute per kilogram of solvent. Okay, not solution, but solvent. Percent by mass is defined, or percent by weight is defined as gram solute over gram solution. So the mass of solute is a percentage of the total mass of the solution. So you can multiply that by 100%. Parts per million is basically the same thing as similar to percent by mass, basically the same thing, except that it is multiplied by 10 to the 6th. Okay, so it's a fraction, the amount of solute in the mass of the solid as a fraction of the total mass of the solution expressed as parts per million. Okay, 10 to the 6 is 1 million. So think of percentage as part per 100. So parts per million you multiply by 10 to the 6 instead of 100%. So if you want to put a unit here, you can say times 10 to the 6 ppm. Okay, 10 to the 6 parts per million. A million is 10 to the 6, so that's essentially a 1. So what you're doing is you're just expressing that fraction as a ppm rather than a percent. Parts per billion is the same thing, except that a billion is 10 to the 9, so you multiply by 10 to the 9. Now, you'll notice that you can also express parts per million as milligrams of solute per kilogram of solution. Why is that? A milligram is 10 to the negative 3 grams, and a kilogram is 10 to the 3rd gram. So that means that is equal to 1 over 10 to the 6, that ratio. Okay, so that's a part, 1 part out of a million. A milligram is 1/1,000,000th of a kilogram. Or you can also say that that's essentially micrograms of solute per gram of solution. Microgram is 10 to the negative 6 grams. Okay, so 1 part in a million. So 1 microgram would be 1/1,000,000th of a gram. And finally, mole fraction is just the ratio of the moles of whatever component you're interested in. Could be a solid, could be the solvent. Okay, divided by the total moles. So if n sub A, if you have a mixture of A, B, C, and so on, divide the number of moles of A by the total number of moles. That gives you the mole fraction of A. One thing to note about mole fractions is if you add up all the mole fractions for all the components of your mixture, those mole fractions should add up to 1. Okay? Here's a simple example. Suppose you have 18 grams of glucose, C6H12O6. You mix it with 200 grams of water. Let's calculate molality, percent by mass, ppm, ppb, and mole fractions. Let's start with the percent by mass, ppm, and ppb, though, because those are easy. All right? So let's start with percent by weight, or mass percent. That's grams of glucose. Doesn't have to be grams. You can make it kilograms as long as you're using the same unit for the mass. over grams of solution. So how many grams of glucose do we have? 18.0 grams. What's grams of solution? It's not 200. 200 is just the water. Okay, so you have to add the water and the glucose. That's the whole thing. So that's 218.0 grams. And multiply that by 100%. So that gives you 18 divided by 218.08256 times 100%. So this is 0.08257, 0.08257 times 100%. Okay, so number of sig figs here, 3 sig figs in the numerator, 4 in the denominator. That means you need to keep 3 sig figs, 0.0825. So that's going to be 0.0826 times 100%. That's going to be 8.26%. Okay. Is that right? Let me just verify my numbers. 18 divided by 218 times 100. Yeah, 8.26%. Okay. How do you get parts per million? Parts per million would be the same ratio, so 18.0 over 218 times 10 to the 6 parts per million. Okay, so that would be equal to, this is ppm of glucose. Okay, it's going to be equal to 0.0826 times 10 to the 6 parts per million. Okay, or that's going to be 8.2612, so that's times 10 to the 4th parts per million. Now you'll notice this is a large number. We generally don't use parts per million when you have numbers this large. Okay, so it's not convenient, but the reason parts per million is defined is sometimes we have to deal with very, very low concentrations, and so if you get numbers like huge numbers like this, it's not a convenient unit to use. Parts per billion, same thing, except you multiply by 10 to the 9, so it's going to be 8.26 times 10 to the 7 parts per billion. Okay. How about molality? Let's do molality. Molality. Molality is defined as moles of solute. So in this case, our solute is glucose, C6H12O6, divided by the kilograms of your solvent, which in this case is water. So let's calculate moles of glucose. If you know the mass, that's the mass of glucose, 18.0 grams. Okay. Basically, you divide it by the molar mass. What's the molar mass of glucose? C6, so that's 6 times 12.01, H12, so that's 12 times 1.008 grams per mole. O6, so that's going to be 16 times molar mass of oxygen is 16. You did this, you should get 180.2. Okay, so 180.2 grams per mole is the molar mass of glucose. Grams cancel out there. That gives you moles. Divided by kilograms of solvent. Our solvent is water, so that's 200 grams. Change that to kilograms, would be 1 kilogram is equal to 1,000 grams, right? So that cancels it out. That gives you your unit in moles per kilogram. So let's do that. 18.0 divided by 180.2 divided by 200. I'm just going to divide that by 0.2, okay? And that should give me 0.499. Why did I divide by 0.2? This thing right here, 200 over 1,000, that's 0.2. So this is going to give me 0.4994. So 0.4994 moles per kilogram. Keep in mind, when we say moles per kilogram, what we really mean is moles of whatever the solute is per kilogram of solvent. Sig Figs, you have 3 Sig Figs here, 4 Sig Figs, 4 Sig Figs, exact numbers, so your answer should have only 3 Sig Figs. So it's 0.499. So this solution we say is 0.499 molal, if you want to write it that way, okay? Or you can just abbreviate it, 0.499, and then little m is the abbreviation for molality. What about mole fractions? Let's calculate mole fractions. By definition, mole fraction is just the number of moles or whatever component you're interested in divided by the total number of moles. So mole fraction of glucose is just, oops, I'm sorry. Abbreviation for mole fraction is X. The symbol is X. So mole fraction of glucose is moles of glucose over moles total. So how do we solve for moles of glucose? We have 18.0 grams of glucose divided by 18.02 grams per mole. Okay? So you divide the mass by the molar mass. That gives you moles. And the total would be glucose and the water. So I already have the glucose right here, 18.0 grams over 18, oops, it should be 180.2, sorry. This is 180.2 grams per mole. Okay, and so 18.0 over 180.2 grams per mole. Cancels grams. Plus moles of water. So this is your glucose. This is glucose, moles glucose. And you need moles of water over here. So how many moles of water do we have? We have 200 grams of water. So I need to change that to moles. So 200.0 grams. Molar mass of water, by now you should know it. 18.02 grams per mole. Okay. H is, you have 2 hydrogens, so 2 times 1.008, and 1 oxygen is 16.00, so that would give you 16 plus 2.016, 18.02 grams per mole is the molar mass of water. So let's add these all up. Calculate. We're going to get 18 over 180.2 at 0.09989. 0.9989. Okay. And the denominator is, your moles are just going to cancel out. Mole fraction is unitless. 0.09989 plus the water, 200 divided by 18.02, that gives you 11.099. Okay? 11.099. Now, you may be asking about Sig Figs here. Alright, this is 3 Sig Figs. Okay, so we'd use at least 4 Sig Figs for a molar mass. We should keep 3 Sig Figs in our numerator, right? But we're going to keep that extra digit there just so we don't build up round-off errors, since that's an intermediate calculation. And then moles, the same thing down here, 3 sig figs, and then moles of water, 200.0. That's 4 sig figs, so 1, 2, 3, 4, and then we're just keeping that extra digit there for safety. Okay. So this gives us 0.09989 over, what's the sum of the two things in the denominator? 11.099 plus 0.09989, that's 11.1989. So obviously I have more sig figs in my numerator. My last sig fig here should be this one right here. And actually this one right here, right? Okay. This is my last sig fig. So I have 4 sig figs in the denominator. So this gives you 0.09989 divided by 11.1989. That gives you 0.003 sig figs, 00892. Okay, 3 sig figs, 00892. That's your mole fraction of glucose. How do you get the mole fraction of water? To get the mole fraction of water, it's just moles of water over moles total, right? So in this case, you're going to put 11.099 over 11.1989, or you can just say it's 1 minus 0.00892, okay? And that should give you your mole fraction of water. Okay. Now, if you know the concentration of a solution and you had a sample of it, so let's say you went to the lab, there's a label on the bottle that tells you what the concentration is. How do you know, how can you figure out how much solute is in there? All you have to do is multiply whatever the known concentration is by the volume of the solution if the concentration unit is of type 1. So for example, if you know percent by weight by volume, okay, you know this is grams per deciliter. You multiply that by the actual volume in deciliters of your sample, then that gives you the grams of solute present. Okay? If you know you're given the concentration in milligrams per deciliter, multiply that by deciliter. The deciliter will cancel. That will give you the amount of solute in milligrams. Similarly, molarity is moles per liter. So if you multiply molarity by the volume in liters, okay, liters cancel out, that will give you moles of solute. Now, if you multiply the molarity by the volume in milliliters, then what do you get? You have moles per liter times milliliter. That's the same thing as moles per liter times 10 to the negative 3 liters. Okay? And 10 to the negative 3 moles is a millimole, so that will give you millimoles. Okay? Think of it this way. Molarity times liters gives you moles. Molarity times milliliters gives you millimoles. So here's a sample problem. Let's say a diabetic's blood glucose level is found to be 225 milligrams per deciliter 2 hours after ingesting 75 grams of glucose. How much glucose can be found in a 5 cc blood sample drawn from this person? 5 cc means 5 milliliters because a cc is a milliliter, so that's equivalent to 5 milliliters. We're just going to treat that number as exact, okay? So if your glucose level is 225 milligrams per deciliter, all you have to do is multiply that by deciliters. How many deciliters do you have to get the actual milligrams, right? So how many deciliters do we have? Well, we know we have 5 mils, so all we really have to do is change your 5 mils to deciliters. So you can say 5 milliliters. I'll change that to deciliter. How do I change milliliters to deciliter? Remember, a deciliter is 100 mils, right? So 1 deciliter is 100 mils, right there. Okay, so milliliters will cancel out, and deciliters will cancel out. That gives you your answer. That would be 225. 225 times 5 divided by 100. That gives you 18 milligrams. Okay? That would be the amount of glucose in a 5 cc sample. Here's another way you can do it. You can say this is 225 milligrams per deciliter. And a deciliter, you can say, is 10 to the negative 1 liter, right? A deci means 10 to the negative 1. Multiply by 5 milliliters. 5 times 10 to the negative 3 liters. Milli means 10 to the negative third. Okay, so you can cancel liters right away there if you want, and you should get the same answer. So that's going to give you 225 times 5 times 10 to the negative 3 divided by 10 to the negative 1, and that should give you the same answer. Alright. Here's another application. Commonly used reagent in the laboratory is concentrated HCl, okay, which is 12 molar HCl. How much HCl is present in a 5 ml sample? Okay, so number of moles. You're given the molarity, so you can calculate the amount of solute, moles of solute. Okay, so you're going to say moles of HCl is molarity times volume. Okay, so our molarity is 12.0 moles per liter. Okay, so we're using milliliters. It doesn't really matter. Moles per liter. And 5 mils would be 5.0 times 10 to the negative 3 liters. Okay, so liters cancel out. That gives you, okay, 12 times 5 is 60. 60 times 10, 2 Sig Figs times 10 to the negative 3 moles. Or you can say that's 60 millimoles. Okay, because 10 to the negative third moles is a millimole. So molarity times volume in mils, 12 times 5, 60. That's 60 millimoles. If you want it in moles, you just go ahead and multiply this out. So in moles, that would be equal to 0.060 moles of HCl. It's a quicker question. Which contains more moles of solute? 10 mils of 0.5 molar sodium chloride or 20 mils of 0.25? Or is it neither? Okay, so you're given the molarities. So to get moles, moles would be equal to what? Moles of solute is molarity times volume. Okay, so let's just multiply 10 times 0.5 versus 20 times 0.25. 10 times 0.5, half of 10 is 5. 20 times 0.25, that's a quarter of 20, that's also 5. So the answer here would be the same. Okay. Which contains more grams of solute? Well, this is similar to the earlier one. You have the same moles, right? We've seen that earlier. Okay. You have 5 millimoles, right? Moles times molarity. This is 5 millimoles in both cases. So 5 millimoles, they both have 5.0 millimoles. Which one has more grams? Then you'll have to convert your millimoles to grams. Okay, so I'm going to say 5.0 millimole times, what's the molar mass of sodium chloride? We did this earlier. Molar mass of sodium chloride is 58.44 grams per mole, right? So multiply by 58.44 grams per mole. Okay. Now, when you do this, mole will cancel out. You'll still be left with a milli there, which is 10 to the negative third. So that will give you a milligram if you don't replace the milli by a 10 to the negative third. But it's really irrelevant in this case. You don't even have to do that because you're just comparing the two. Okay, you're not asked for the actual amount. So here you have 5 millimoles this time of sodium hydroxide, and molar mass of sodium hydroxide is 40.00 grams per mole. Again, we've seen that earlier. So which one will have more grams? The one that has a larger molar mass. So the correct answer in this case is A. Now, what about if you have a type 2 concentration? How do you determine the amount of solute? Well, just multiply the known concentration by either the amount of solvent or solution, depending on which one you use in the definition of the concentration. So, for example, molality, that's moles of solute per kilogram of solvent. You multiply that by the kilogram of solvent, that gives you moles of solute. Okay. If you have a mole fraction, whatever the mole fraction is, multiplied by the total moles, okay, that gives you moles of component. Remember, mole fraction of A, for example, is moles of A over moles total. So if you multiply total moles by the mole fraction of A, that will give you the number of moles of A. Grams of solute, whatever grams of solution you have, just multiply that by the percentage, the mass percent. Okay? If you want if you're given the ppm, okay, ppm, if you remember, is milligram of solute per kilogram of solution. So you multiply that by kilogram of solution, that will give you milligrams of solute. And ppb, if you recall, is micrograms per kilogram, okay, of solution. So you multiply that by kilograms of solution, that will give you micrograms of solute. Here's an example. Solution was prepared by mixing 2 grams of an unknown compound with 20 grams of water. And then let's say you did an experiment and you found that the molality of the unknown aqueous solution is found to be 0.5 moles per kilogram. How many moles of solute are in the sample? Okay, so we're given molality, so 0.50 moles of solute per kilogram of solution, solvent. Okay, how many kilograms of solvent do we have? That's 20 grams of water, so let's change that to kilograms. 20.0 grams of water, our solvent, times 1 kilogram over 1,000 grams. Grams cancel out, kilograms cancel out. That gives you moles of solute. Okay, so this is moles of solute, and that's going to be half of 20. That's 10 divided by 1,000. That should be 0.01. Let's just make sure. 0.5 times 20 divided by 1,000. 0.01. Okay, so this is going to be 0.01. 2 Sig Figs, 3 Sig Figs, so I need 2 Sig Figs here, 0.010 mole. Okay, so the correct answer here is B. Now, it's a follow-up question. What's the molar mass of this unknown compound? What's molar mass? Grams per mole, right? Molar mass is the mass of a mole. So anything per mole would be grams over moles. Okay? So how many grams do we have? We're given 2 grams of your unknown compound. So 2.00 grams divided by number of moles. We just figured out our number of moles of our compound. Our solute is 0.010 mole. So that should give us 2 divided by 0.01, 200. 200 grams per mole. Number of Sig Figs, 3 Sig Figs, 2 Sig Figs, so this should have 2 Sig Figs. So it's best to write this as 2.0 times 10 to the 2 grams per mole. That would be the molar mass of your compound. Okay. Let's talk about preparing solutions in the lab. Let's say if you want to make a solution in the lab, obviously one of the things you want is you want a particular concentration. You want to decide beforehand what concentration you want. And you also want to decide how much of the solute you're going to use, or how much of the solvent you're going to use, or how much solution you want. Okay, so in the remember, when we define concentration, you have amount of solute or solvent in the numerator over the total or the solvent in the denominator, right? So if you know what concentration you want, you have to decide on one of these other two, and then you can figure out the other one. So you use the defining equation to calculate. So you either decide on the value for the numerator or the denominator, and then you figure out the other one. So you use the defining equation to calculate the other one. And then once you have the values for the numerator and the denominator, then all you have to do is convert those to measurable lab quantities, typically grams if you're dealing with solids. If you're dealing with a liquid, it's not a good idea to weigh liquids, so it's best to look up the density of the liquid and convert the grams that you need to milliliters, okay? And use what's called TD glassware. You have glassware that's labeled TD. TD stands for to deliver. So those are glassware that are specifically calibrated for dispensing precise volumes of liquids. Now, if your desired concentration is of type 1, remember type 1, your denominator would be volume of solution. What you would have to do is put your solute in a piece of glassware that's marked TC. TC means to contain. An example of that is a volumetric flask. So you put however much solute you need there, and then just bring it up to the mark. Add enough water to, if you're doing an aqueous solution, to get to the correct total volume. Okay? Don't make the mistake of just adding up volumes, because volumes generally, like if you're dealing with liquids in particular, they don't usually just add up to your desired volume. You have to use a piece of glassware that will actually tell you how much total volume you have. Just to illustrate, let me show you the volume, a volumetric flask. This is an example of a piece of glassware. So let's look at images of volumetric flasks. There's plenty of those on the internet. Okay, so it comes in different sizes. You'll notice these flasks have a marking right here. That's called a fiducial mark. So these are designed to contain. So if you look at the label here, you'll see a TC on the label. This one in particular, for example, will hold, if you bring it up to this mark, you'll know that you have a total volume of 1,000 mils. This one in particular will bring it up to 500 mils, and so on. Okay? So that's TC, to contain. An example of a piece of glassware that's intended to deliver would be a pipette. So a pipette, let's look for images of pipettes. Okay. Oops. These are pipettes, and so they come in different sizes, so you have to fill them to that marks. For this particular type of pipette, it's designed to deliver a particular volume, or you can use a graduated cylinder also. Okay, you may also use what's called a burette. Okay, this one, these are some calibrated pipettes right here, so there are markings there that allow you to control how much volume you want to dispense. Okay, and a burette is also something that you could use to deliver liquid. So these are burettes, examples of burettes. Okay, and so this stopcock right here, when you turn this on, when you turn this 90 degrees, this right now is on right now. If you turn this 90 degrees, it shuts off the liquid. So the way this is set up is, if you have a liquid in here, and this is open, the liquid will flow out. So you measure, you read the level of the liquid in the burette before and after you've dispensed your liquid. So for example, if your liquid level starts out at 22 and ends up at 24, that means you've delivered 2 milliliters. Okay? So let's look at an example here. Let's say you want to prepare 500 milliliters of 0.5 molar sodium chloride. So what's our desired concentration? 0.5 molar, right? So we've decided we want 500 mils, so that's the denominator in the defining equation. Remember, molarity is moles over volume, right? So number of moles is the numerator, volume in the denominator. So we decided we want 500 mils, so that's 0.5000 liters. So what's our numerator? Multiply molarity times volume. So 0.5 times 0.5, that should give you, okay, 0.500 moles per liter times 0.5000 liters. Okay, so that gives you 0.25. 3 Sig Figs, 0.250 moles. Okay, that's the moles of solute. Well, there isn't a thing in the lab that tells you how many moles you have. We don't have a mole meter, so you have to convert it to something you can measure in the lab, and that would be grams. So you had 0.25 moles of sodium chloride. You have to change that to grams. So 0.250 moles sodium chloride. You're going to need the molar mass. A mole of sodium chloride weighs 58.44 grams. That's the molar mass. Oops. Wrong conversion. 58.44 grams for 1 mole. So moles cancel out. That gives you how much? A quarter of 58.44. 14.61 grams. Okay? 3 Sig Figs, so I only need 14.6 grams. So what do? I go to the balance, I weigh out 14.6 grams, okay, and I put it in a volumetric flask. So I'm going to transfer 14.6 grams of sodium chloride. So it's going to be I'm going to have a salt here, and then I'm going to add enough water, okay. I'm going to add enough water to make it 500 mils. I'm going to use a volumetric flask that has a 500 ml capacity. If I bring up my solution, my water level there to that mark, I know that I have a total volume of 500 mils. Okay, so grams of solute here is 14.6 grams. Amount of solvent here, it's not 500 mils of water, it's enough to bring the total volume to 500 mils. All right, so that's how you prepare a solution. Now, dilution is another way you make a solution. It's a useful method for preparing solution. Dilution simply means adding more solvent. And it's very useful for preparing solutions that have very low concentration. So solutions that have a very low concentration are said to be very dilute. So diluting simply means lowering the concentration. Okay? If you add more solvent, you are lowering the concentration, and referring to the concentration of the solute. Why is this important for very low concentrations? The reason is typical balances in the lab, okay, weighing scales in the lab, you call them balances, okay, balance. They're not sensitive enough, may not be sensitive enough for very small masses. Okay, typical balance, one of the most sensitive ones in an instructional laboratory, will have an uncertainty of at least 0.2 milligrams. Okay, so if you have to weigh something less than that, then you're out of luck. Okay, some substances are also more readily available in solutions. For example, hydrogen chloride is a gas. Okay, you don't want to be handling that. It's more readily available as a 12 molar solution, concentrated HCl. it's already mixed with water. It's 12 molar. So you need to prepare it from, you prepare solutions of HCl from a stock solution that is 12 molar. Okay? So here's an example. Solution A is 10 mils of 0.1 molar sodium hydroxide. So let's say you have, here's a graduated cylinder, you have 10 mils of 0.1 molar sodium hydroxide. And to that, you prepare solution B by adding to that enough water to bring it to 100 mils to get solution B. Which of the following is true? Solution A contains more sodium hydroxide. Solution B contains more sodium hydroxide. Solution B has a higher molarity, or none of the above. Well, what are we doing when we are diluting? You're just adding more solvent, more water. You're not changing the amount of sodium hydroxide. So A is false, B is false. What happens to the molarity? Well, your volume has changed. Molarity is moles of sodium hydroxide over the total volume of solution, right? Well, your number of moles of sodium hydroxide doesn't change. No change here. But your volume of solution increases. If you have a bigger denominator, the molarity goes down. So your molarity would be lower, not higher. So correct answer for this one would be none of the above. Okay, how about this question? Which of these most likely needs to be prepared by dilution? 100 mils of 0.1 molar sodium chloride or 2 liters of 1 times 10 to the negative 6 molar sodium chloride? Okay, you can see this is a very low concentration. You can actually calculate the moles here if you want. 100 mils times 0.1. Okay, let's figure out the number of moles. 0.1 moles per liter of sodium chloride times 100 milliliters. Milli means 10 to the negative third. So 0.1 times 100 times 10 to the negative third. That gives you 0.01 mole. Whereas the other one, you have 2 liters, so but we have 1.00 times 10 to the negative 6 moles per liter, multiplied by 2 liters. That gives you 2.00 times 10 to the negative 6 moles. This is a very small amount. In fact, how many grams would that be? Okay, 2.00 times 10 to the negative 6 moles of sodium chloride multiplied by the molar mass. Sodium is 22.99, chlorine is 35.45, so that's 58.44 grams per mole. And that gives us, let's see, 2 times 10 to the negative 6. So 2 times 10 to the negative 6 times 58.44, 0.0001. Okay, so that's a milligram right there. So it's 0.116 milligrams. 117. Okay, that is very hard to measure. Your most sensitive balance is in the typical instructional lab, analytical lab would be sensitive to 1/10 of a milligram. Okay, so that's below the sensitivity. That's right around the sensitivity of your analytical balance. Okay, so what you would do is you need to make some. So the answer to this question then is this one right here, B. You're going to have to do dilution. You make a solution that's more concentrated, okay, call that your stock solution, and so from that stock solution you can do a dilution. You can do a series of dilutions, okay, it's a technique known as serial dilution to make progressively dilute or progressively lower concentrations. All right, here's a practical laboratory problem. You have a stock solution that's 12 molar HCl in the laboratory, that's concentrated HCl. And you want to prepare 500 mils of 0.5 molar HCl. How much stock solution would you need? to dilute to 500. So you've decided you want 500 mils, and you want that to be 0.5 molar. Okay, so number of moles you need is 500 mils, 500.0 times 10 to the negative 3 liters. Molarity, let's do molarity times volume. So 0.50 moles per liter times, that's half a liter, so 0.5000 liters. Okay, so that's molarity of the stock, the final solution, right? The desired molarity times the desired volume. So that would be your final molarity and the final volume that you want. Well, that's going to have to be equal to the moles you can get from the stock. So moles, molarity of the stock solution times the volume of the stock solution that you're going to need must be equal to that. So in other words, when you're doing a dilution, you can say M1V1 equals M2V2. This is called the dilution formula. What this is basically saying is number of moles of solute in the stock solution must be equal to the number of moles in the final solution, because once you've taken the stock, all you're doing is adding more water. So what's the molarity of our stock solution? It's 12, right? And so your volume of your stock solution is what you need to find out. How much of the stock do you need to dilute to 500 mils? So let's solve for your volume of stock. Okay, M stock V stock equals M final V final. So this is going to be equal to M final V final over molarity of the stock. Right, so our final molarity, desired final molarity is 0.50 moles per liter. The final volume that we want is 500 mils. I can make that 500 mils if I want to, because as you can see, the units will just cancel out. Molarity in this case is 12.0 moles per liter for the stock. You can see that moles per liter cancels out. I will have my answer in milliliters. If you want it in liters, then you change this 500 mils to liters. Make that 0.5 liters. So 0.5 times 500 divided by 12. That gives you 20.8. Okay, so 20.8 milliliters. Or, since we only have 2 Sig Figs, it's 21 milliliters. So what do? What you do is you take 21 mils of your stock solution plus enough water to bring your total volume up to 500 mils. Word of caution, practical information in the lab. Whenever you're diluting concentrated acids in the lab, always add acid to the water. Okay, acid to water. That means don't just take 21 mils of HCl and then add water to it. You generally do not add water to a concentrated acid. When you have a concentrated acid, add acid to water first. So what you do is, if you have a volumetric flask, for example, you can put some water in there. Okay, water first, and then you put your 21 mils of acid, concentrated acid. So your concentrated acid would mix, and then dilute to the mark to 500 mils. Okay, you can add water to acid if the acid has already been diluted. Otherwise, you don't do that. Whenever you start with concentrated acid, if you want to dilute it, add it to the water first. A before W. Okay, here's another question. Rubbing alcohols, typically the one you can buy at the store, is 70% by volume isopropanol in water. How would you prepare 2 liters of 0.1 molar isopropanol in water? Isopropanol is C3H7OH. Okay, how much of the rubbing alcohol would you need? The density of pure isopropanol is 0.786 grams per mil. So here's a strategy you can use. You calculate the moles of isopropanol that you need first. And what information do we need for that? Our desired solution is 2 liters of 0.1 molar. So moles isopropanol I'm just going to call it ALC for alcohol, okay? Moles of alcohol equals 0.100 moles per liter of alcohol times 2.00 liters. That cancels. So that gives you 0.2, let me make that blue, 0.200 moles of alcohol. Okay? Now, you change that to something you can measure in the lab, which is grams. So 0.200 moles of C3H7OH, change that to grams. Grams per mole. What's the molar mass of isopropanol? Let me do a quick shortcut here. Let's just go to molar mass C3H7OH. I've done this search earlier. Okay, it's 60.1 grams per mole. Okay, if I need more Sig Figs, it's 60.095 grams per mole. 60.095. So how much is that? 0.2 times 60.095 gives me 12.019. So 12.02. Okay. Keeping in mind my last Sig Fig is that 0 right there, grams. Okay. Isopropanol is a pure isopropanol is a liquid, so it's preferable to measure its volume rather than weigh it. So what you do is you change that to volume. Density is mass over volume. So if you want to solve for the volume, volume is mass over density. So 12.02 grams, keeping in mind that last Sig Fig there is the first decimal place, divided by the volume, which the density, which is 0.786 grams per mil. Okay, and that should give you how much? 12 divided by 0.786. It's 15.29, 3 Sig Figs, so that's 15.3 milliliters. So what I'll need to do is I find a volumetric flask. I find a container that can hold 2 liters. So that's a 2-liter mark right there. I am first going to dispense 15.3 mils of, that would be pure, okay? I don't have pure. Sorry. Okay, not there yet. That would be pure, okay? So this is pure. But what I have is rubbing alcohol, which is only 70% isopropanol by volume. Okay, let's treat that 70% as exact. So we say this is 70% of the volume you need, of the volume of isopropanol needed, of rubbing alcohol needed. Okay, since we don't have pure isopropanol, we have rubbing alcohol, which is only 70%. So you say 15.3 mils is equal to 0.70, that's 70% of the volume of the rubbing alcohol that you need. Okay, so the volume of the rubbing alcohol that you need is equal to 15.3 divided by 7.0, and that should give you 21.9 milliliters. So now what I do is this. I take a volumetric flask with a 2-liter capacity. I put in 21.9 mils of rubbing alcohol, and then add enough water to bring it up to 2 liters. Okay, and that will give me a solution, a 2-liter solution that is 0.1 molar isopropanol. Okay, this might be a good time to stop.